Welcome to Lesson 13. In this lesson, we will have a look at security concerns and considerations for Solidity language. Here's a really good quote about security relevant for this lesson, and it says, "While it is usually quite easy to build software that works as expected, it is much harder to check that nobody can use it in a way that was not anticipated." So while Solidity does not look like a hard language to learn, and it is not, there are many bugs lurking just around the corner. We will have a look at common pitfalls in Solidity programming language and ways to go around them. So the first common pitfall is that everything you use in a smart contract is publicly visible, even local variables and state variables marked as private. Read access can be hardened by using encryption, and only read access can be truly limited. Reentrancy is another common pitfall, and it's a type of attack where functions can be called repeatedly before the first invocation of the function is finished. And the way to prevent it is to not perform external calls in contracts before making sure that all internal works have been finished. We will have a look at an example of that soon, and this is also how the famous DAO attack was executed. Another common pitfall is the gas limit, and loops are especially prone to cause that, especially loops that do not have a fixed number of iterations. For example, loops that depend on storage values have to be used carefully, since they can grow in size and make gas consumption hit the limits. Another common pitfall to keep in mind is that Ether send function can fail. So when sending money, your code should always be prepared for the send function to fail. The final common pitfall to keep in mind is the timestamp dependency. Never depend on timestamps for critical parts of a code because miners can manipulate stamps. Now let's have a look at some of the most common security recommendations. One way to make smart contracts safer is to fail early and to fail as loud as possible. This can be done by using exceptions properly. In the example below, we use require and assert exception handlers to check that the name argument, like here, is valid and that the corresponding record in payout, like so, maps to a non-zero value. And if it doesn't, if none of the exceptions are thrown, we simply return the payout of the corresponding name. Now, function modifiers can be especially useful to make code more readable and still allow it to fail early and loud. In the example below, we have onlyBy modifier, which is used by changeOwner function to only allow the owner of a contract change it to another owner. So here we have a function modifier onlyBy, which takes a parameter account of data type address, and it makes sure that the message sender and the account passed to this function match. And we apply this modifier for the changeOwner function by passing the owner parameter to onlyBy function modifier. And what this does is that it only allows the owner of this contract to execute the changeOwner function. The next security recommendation is to make use of checks effects interactions pattern. Checks effects interactions pattern is a simple and well-recommended coding pattern where you first check all preconditions by using assert and require. Then, make changes to contract state, and only then, finally, interact with other contracts via external calls. Now consider the example below, which introduces attack surface for a reentrancy attack. In this example, the recipient could call withdraw multiple times before withdraw is finished executing, and as a result, get multiple refunds. So as you can see here, we have a function withdraw, and it has another function within, send, which sends a given amount of shares to the sender of this message. Now this function is an external function, and while it's executing, the recipient could call this withdraw function again, over and over, and get the refund multiple times. Only once this function is finished executing, we reach this line where we assign the shares of the message sender to 0. As you can see, this is quite problematic, and this is how reentrancy attack works. But by using checks effects interactions pattern, we can avoid this problem, as in the example below. So before transferring the funds, we make sure that the receiver has any funds to receive at all, like here. And if he or she does, we set his or her balance to 0, and only then make the token transfer. So even if withdraw is called again before token transfer is finished executing, the corresponding account balance will already be set to 0, like we did here, and only then, after it's set to 0, after the balance is set to 0, we make the token transfer, and this will prevent the reentrancy attack. Now, another security recommendation is to restrict the amount of Ether or other tokens that can be stored in a smart contract. So if your source code, the compiler, or the platform has a bug, these funds may be lost. But if you want to limit your loss, you can just limit the amount of Ether stored in the contract. Also, attackers are less likely to try to mess with contracts with low balances and will instead opt in with contracts holding millions in funds. So here we have an example of a limit funds contract, which has a limit of 5,000. So if we try to deposit some funds to this contract, and if we go over the limit, it will throw an exception. So this makes sure that the balance does not go over 5,000, because this is the limit that we are comfortable with to keep in this contract. Another security recommendation is to keep contracts small and easily understandable. So single out unrelated functionality in other contracts or into libraries. Also, general software engineering recommendations apply, such as limit the amount of local variables, limit length of functions, and document all the functions so that others can see what your intention was and whether it is different than what the code does. Now, the final security recommendation is to mind Ethereum virtual machine limits. The Ethereum virtual machine has a fair chunk of limits that one should be mindful of. For example, integers can easily overflow or underflow, a gas limit could be reached, and all the work done until that point will be reverted and thus lost. So here we have an example of a problematic code contract which calculates payouts for affiliates stored in the affiliates array and then sends payouts to them. And the payouts are calculated in the calculate payout function, which we assume is quite expensive to compute. So while the above example looks simple enough, it hides two potential flaws. First, since unsigned integer 8 is the lowest sufficient data type to hold value 0, this is what variable I will be initialized to, as you can see here. However, since unsigned integer 8 is made up of 8 bits, it can only represent 255 distinct values. Thus, if affiliates array goes over 255 elements, we are going to experience integer overflow and as a result never terminate the loop. This can be fixed by declaring unsigned integer, which defaults to 256 bits and thus can store huge values. Another problematic area with the above example is potential gas limit. Imagine a scenario where we are calculating payout and sending it out for hundreds of affiliates. We have processed 90% of them, but then ran out of gas. As a result, all the work we have done up to that point will be for naught, because Ethereum virtual machine will revert all the changes to the state in which it was before calling this function. Now, the best way to go about the gas limit problem is to separate the payout and calculation functions and first do the payouts calculation and only then do the payouts. Then if either one fails, at least not as many resources will be lost. So as you can see here, first we calculate the payouts separately and store the payout that needs to be paid out in a payouts array. And then we have another function, payAffiliates, which only has to retrieve the amount to be paid to the affiliate and then sends that amount. So this is the separation of concerns that is really useful in this situation. So this is it for security recommendations. There are many more, and you can expect the resources area of our GitHub repository to see more, but this should give you a solid ground to at least be familiar with the security concerns in Solidity. In the next lesson, our final lesson, we will learn about the differences between deployment on test network and main network, and I will deploy the dummy token contract on the main network and show you how to interact with it. I'll see you there.